You're a very unusual class. I've never taught a class before where the students migrated to the front. That's really fantastic. Thank you. I take that as a huge compliment. So it's so nice to have everybody, instead of hiding in the back row. Thank you. Okay. So before we fall inside the black hole, and there's going to be a nice movie at the end showing you what it will feel like. Probably none of us will ever experience it, but we can imagine. I just want to point out one thing. So at the end of during the last lecture, we used an equation like this for the orbit of a particle. And then I pointed out that for a massless particle, this term isn't there, right? And that was because from the g mu x dot is 0 for the massless particle. And this goes away, and I think this goes away as well. But what it means is that the potential, the effective potential for a photon, instead of looking like this guy, remember this guy had the minus 1 over r cubed, the plus 1 over r squared, and the minus 1 over r. All right, so for a massive particle, you have something like this. For a photon, this guy is gone, so you just have that. Okay? So the question is, can the photon, does a photon have a circular orbit around a black hole?
Yes. Yeah.
And it does, and it's just here. And what's the radius?
R minus.
Pardon?
RS?
Not quite. I calculate the maximum of this potential. Right, so differentiating this, I get 2j squared over r cubed plus 3 rs j squared over r4 equals 0. So r is 3/2 rs. Okay, that's this point where dv dr is 0. So there's no force there. And so if you put a particle exactly here at 3/2 rs, which is, of course, 3gm over c squared, the photon will orbit indefinitely. Okay, it's unstable orbit, but nevertheless, you shine a torch. If you're standing, 1.5 times the Schwarzchild radius and you shine a torch, actually the better way of saying it, which you'll see in the video, is you stand at 3/2, stand at 3gm over c squared and just look this way. What will you see?
Your
back of your head. Okay. Because the light that comes off the back of your head will go around the black hole and you'll see yourself. So you don't need a mirror if you have a black hole. Okay. So very good for hairdressers. The best hairdresser in the universe will be located at 3/2 the Schwarzschild radius. How does it look? Yeah, it's fine. Okay. So I just did that because they're going to refer to it in the video. Let us now do a simple exercise, which is we fall radially into a black hole. Okay, and in this case, J is 0 if it's radially. There's no angular momentum, and then the equation we have to solve is just dr dτ squared plus 1 minus rs over r equals e squared. So I just take this equation. I'm now doing a massive particle, so I need these terms back again. But what I'm going to do is start the particle at rs. Okay, so it's a little bit weird because we know that for r less than rs, r is really a time-like coordinate. But anyway, let's just do the algebra. If we start off at r equals rs with dr d tau equals 0, that means that I'm literally, starting at the Schwarzchild radius. I'm starting here with no velocity. So I just drop a particle from the Schwarzchild radius. It will fall radially to the center of the black hole. Okay, so that means that E equals 0, right, from this equation. If R is Rs, this is 0, so E is 0. And so we can easily solve that. What we get is that tau is integral dr. Just integrating this equation, I divide by this factor. Keep in mind that r is smaller than rs, so this number is always bigger than 1. So this is r over rs minus 1. And I'm going to integrate from rs, because that's where I started, down to some particular r. This would give you the time it takes to get to some r. Okay, so this is the proper time to reach r less than rs. Now the total time, the time to hit the singularity, this is the proper time, so it's the time you would measure on your watch, would be this integral, 0 to rs of root r over rs minus 1. So,
RS over R.
oh, sorry, thanks. Rs over r, yeah, it's bigger than 1, that quantity is bigger than 1. Rs over r. And the integral is finite because it has a 1 over square root singularity at r equals 0. At r, well, it has a, well, it's obviously equal to integral dr square root of r over square root rs minus r, 0 rs. So the integrand diverges at r equals rs, but it's a square root, so the integral is finite. And so we can do this integral easily enough. Let us change variables to r as sine squared theta. And then the numerator becomes, actually r equals rs sine squared theta. The numerator becomes, I get 2 cos theta sine theta. This gives me another factor of sine theta. So, and I get an overall rs. So 2 rs. The denominator, rs minus r, I'll get the overall rs, and then 1 minus sine squared theta. Square rooted gives me cos theta. So I just get this integral, sine squared theta, sum 0 to pi over 2. Because r equals rs when theta is pi over 2. And then this integral, sine squared, is 1 minus cos 2 theta over 2. The 2's cancel. Integral of cos 2 theta gives 0. And the integral of this theta over 2 gives me rs pi over 2. And so the time, survival time, let's say, equals pi rs over 2, which is just pi GM. Okay, and if I want to restore units, this is a time. So the radius would be a GM over c squared, but then if I take the radius and divide it by c, I get a time. So it's GM over c cubed. And so this turns out, you put the numbers in, this is 10 to the minus 5 mass over the solar mass seconds. So if you fall into a one solar mass black hole, you last 10 microseconds, okay, before you hit the singularity. If you fall into the one in the Milky Way, much, much better. You last for 40 seconds, okay, for 4 million solar masses. So quick question. Is this, can I survive any longer than this? Sorry, go ahead.
Yeah, I was going to ask about the limits of the integral.
Yeah.
Why is it because we're starting at RS and ending at R. Should it be there?
Yes, so you'd like them to be this way around?
Yeah. And that introduces a minus sign or tau.
You can do that if you want. Yeah, let me think. Let me think. Where did we get this from anyway? We got it from here, right? So the point is, when you take the square root of this equation, there's a plus or minus sign. Mm-hmm. You have to decide which sign to take. Okay. So we have d tau equals dr. So I take this stuff over here and multiply by d tau, and so I get square root of rs over r minus 1, but I have a plus and minus. Okay. So because I want dr to be negative when d tau is positive, so I write it this way. Okay. And then the r goes from rs to r. But of course, I can flip the limits, and then it goes to plus. Okay? So very good to be careful with all these things, because actually the best way to think about integrals is always as contour integrals, like you're doing complex analysis, and the sign matters. And so, anyway, this comes up many, many times. Okay, so that's very interesting, but what happens? So is there anything I can do to last longer than this amount? If, for example, I assumed I was traveling radially, if I travel with some angular velocity, would that help? So if I have a non-zero angular momentum, if I start here and I spiral in, could I last longer? So I'll let you think about it. You have to bear in mind, so just think about that, whether I would last any longer if I had some orbital motion as well. All right, so this is a little bit fishy because we're dealing with radii less than the Schwarzchild radius, but the Schwarzchild metric was singular at Schwarzchild radius, so I need to understand that before I take this too seriously. So let's now discuss the geometry of Schwarzchild. And we'll see things get really very interesting when we try to make sense of the geometry for our radii less than the Schwarzchild radius. So to remind you, the line element is this. where alpha var is just 1 minus rs over r. Okay, so what happens at r equals rs? As I've said before, for r less than rs, r is a time-like coordinate. Okay, and that means if I keep all the other coordinates fixed and I just change the radius, then I'm moving in a direction which is time-like because this coefficient is negative and this one is positive, so r is the time direction, dr is the time direction in the space-time. And so the Schwarzchild is not static. Static means the metric is independent of time, but if the time-like direction is r, metric depends on r, then it's obviously not static. It's much more like a waterfall. So when you fall through the Schwarzchild radius, it's as if you're on a waterfall. The waterfall is taking you to the singularity, and there's absolutely nothing you can do because the flow of the water is faster than the speed of light. So you can't avoid hitting the singularity. And actually, if you do this calculation, you'll see that traveling in an angular direction only makes your journey shorter, right? I mean, in the limit where I take this trajectory going at the speed of light, my proper time is going to be 0 because I'm nearly null. Yes?
So if r is time-like and
Yes.
t is space-like,
Right.
do you move backwards and forwards in time as though you're walking back and forth in space?
Yeah.
So you
T is the
you
time-like
just never
variable.
really die then. So you have that 40 seconds if you're in the center of the Milky Way, and then just like go to the edge and then come back. And then
No, unfortunately not. That would be really fun.
like
But
space going back and forth in time. Like
yeah, unfortunately, coordinates are not really physical things. So we don't live in T. We live in the time-like coordinate. And so when R becomes time-like, our clock would measure R, not T. And R is going one way to the singularity. Okay, so that's what happens is as you cross the Schwarzschild radius, your clock stops measuring. Well, it wasn't really measuring T anyway, it was measuring tau. And the relationship between T and tau becomes pretty singular at this point, right? At E equals 0. This is 0, so let's see. Yeah. Anyway, we'll do all this in detail, okay? So these are the right questions to ask. What the hell do these coordinates mean if they don't mean what I thought they meant? All will become clear. Okay, so there's a wonderful story about how this was unraveled, what this metric means, and it wasn't until the late 1950s when it was worked out what this actually means, that R can change from space-like to time-like. And basically it means it's a lousy coordinate. You can always, if you have a metric and you change coordinates to some bad coordinates, singular coordinates, like with polar coordinates on a sphere, the metric has singularities there, just like we saw for a sphere at theta equals 0. The metric determinant is 0, so it's not invertible. And here we have similar, this problem at RS is a coordinate singularity. So we're going to unravel that by working through what this means. Okay, so to understand this, let us, to begin with, let us think about radial light signals or null trajectories. Okay, so we think there are massless particles like the photon, and let's watch what photons do in this space-time. And that was the thinking that led to the understanding of what this metric actually means. So we just think about radial light rays. And so they satisfy ds squared equals 0. We just ignore this part of the metric because d theta and d phi are 0 if you're moving radially. And so this means that dt is plus or minus dr t equals plus or minus dr over alpha of r. Okay, so I just set ds squared equal to 0 for a null trajectory or a massless particle. And this is how, these are the two solutions to that equation. So this is dt plus or minus, this is dr times 1 plus or minus dr times 1 plus rs over r minus rs.
Sorry.
Mm-hmm.
There's something I didn't understand because Schwarzchild, for example, if we change to some other coordinates, we can find time-like coordinates inside the horizon, right?
Yes.
So why isn't it static?
Why isn't it static inside? Okay, let me think about it. Well, static would mean that there is a symmetry of the metric. And that symmetry would correspond to a time-like displacement. There is a symmetry in the metric. It's a symmetry t goes to t plus constant. Okay, but t is not time-like inside r equals rs.
Yeah, but if we are in other coordinates, for example.
We'll go to some other coordinates. But all I can say is that the argument that this is static fails inside r equals rs.
For every coordinate?
I didn't say that.
Oh.
We'll go to some other coordinates which are good at r equals rs, but you will see that the metric will not be static inside rs. Okay, so we want to find these other coordinates which are good inside r equals rs. But what we do is think of quite a physical problem that I send light rays into the black hole or coming out of the black hole. So let's see, did I do this algebra correctly? This is, yes, so this quantity is r over r minus rs, right? And then if I divide by r, that is 1 over 1 minus rs over r. Okay, so these are the two trajectories, and we can sketch them. So here is t, and here is r. And I'm still going to use these t and r coordinates, but we have to bear in mind there's something fishy at r equals rs. So to r equals rs, let's draw a line to note the fishiness. Okay. Now, if I'm a long way away from the black hole, r is very large. This factor is nearly 0. And so what I have are ingoing and outgoing null rays. Okay, so dt can be minus dr for this one. dt equals minus dr. And this one is dt equals plus dr. As dr and dt are both positive here, dr is negative there. Now, what happens if I move into... Yeah, in fact, you know that when I include the other dimensions, I would have a picture like this, that there will be a light cone, right? So I can sit here relative to the black hole, and there should be a light cone. These are the inward going, and those are the outward going light rays. Now, as I move towards this R equals Rs, you notice that the dt, as R tends to Rs, this number gets very big. And so the coefficient of dr gets bigger. So the light rays steepen. So they look more like this. Not at 45 degrees anymore. Okay, so if I follow a light ray, let's imagine I follow one from out here. The light cone is a bit wider. It comes in, and then it comes like this, and it just steepens, and its slope goes to infinity, and so t goes to infinity. All right, so t goes to infinity for the ingoing light ray. Okay, and I can't describe it any more than that. I can just say that at t equals infinity, the light ray just reaches R equals Rs. And likewise, an outgoing light ray would come from Rs and then steepen and end up going at, so this would be outgoing light ray, and this would be an ingoing light ray. Okay, so I can never see anything inside the black hole because the light I'm looking at came from t of minus infinity at R equals Rs, and I'm just receiving it now. So I cannot possibly see beyond there. What about inside the black hole? Well, just do the same analysis, and you'll see that inside the black hole, R is the time-like direction. So my light cone actually looks like this, right? For R less than Rs, okay, it looks this way because now R is the time-like direction and T is a space-like direction. So I need to combine the T with the angles to have the spatial cross-section of the light cone. And when I go towards R equals Rs, this light cone flattens like that. Okay, the angle goes nearly vertically. That's not very well drawn. Let me draw that again. So the light cone here would look like this, and then crossed. Okay, so an ingoing light ray would do this and hit the singularity. You can see at R equals 0, dt is exactly 0. So that's telling you that the slope, so dt dr is 0. So it's telling you the slope. In fact, I should have drawn it. Let me draw it a little better. Over here, it's nearly at 45 degrees. And the light is coming in like that. But actually, as I tend to the singularity, this guy closes as well. And here, when you hit the singularity, dt dr is going to 0. The slope of that curve is going to 0. Okay, you see that from here. So if we follow a light ray, it sort of zooms up here, and then there's another light ray, which is coming in from up here and hitting the singularity. And likewise, there's one coming from the bottom and hitting the singularity that way. Okay, so that's the set of all light rays. And now we're going to find some really peculiar properties of these light rays. You see, I want to connect this ingoing guy with, for example, with this ingoing trajectory. If this trajectory falling into the black hole connects to that one, what strikes you as funny about that? See, T is going forward in this part, and backward in this part. Okay, so t is decreasing. And likewise, if this one comes from there, t is decreasing here and increasing over there. So whereas both of these trajectories are going forward in time on this side, when we go on this side, if I trace this guy back to here, then this direction in dr, increasing dr corresponds to decreasing. See, yeah, obviously increasing dr corresponds to decreasing t. Okay, so anyway, there's some puzzles there. But we're not going to take these coordinates too seriously because the metric is singular at r equals rs. So the idea now is to change coordinates to coordinates which are not singular, in which the metric is not singular, in which the metric is non-singular at r equals rs. So this turns out to be quite easy to do. And the idea is the following. Let's integrate this equation. This is an let's call that 1. So let's integrate 1 to find the light ray. And it's an easy integral to do. T is plus or minus r plus rs log r over rs minus 1 plus constant. And this is for r bigger than rs. And it's equal to plus or minus r plus rs log 1 minus r over rs plus constant for r less than rs. Okay, I have to arrange the argument of the log so that it's positive, so that the log is a real number. If I just use this formula and let r go to less than rs, the argument of the log would be negative, and the log would generate an I pi. Right? So I have to flip the sign of the argument for this to be meaningful, but both of them are meaningful as long as r is in the relevant region. So in particular, the ingoing light ray has t equals minus r minus rs log modulus r over rs minus 1 plus constant. And the idea of the new coordinate, so you see t is minus r. Let's just have a look at this one. So, so as r increases, sorry, have I got that? Sorry, I've got, it should be a plus. T, no. Ingoing, t is minus r. Yeah, t is minus r. That's right. So t is larger negative as r is positive on this curve. And as r decreases, t becomes less negative, right? And then as r tends to rs, the argument of the log goes to 0. So the log of a small number is negative. And so this minus log term diverges to plus infinity. Right? So this is the ingoing light ray. It's described by that equation. And now, as I said, we want to change coordinates. We want to change coordinates to ones which, in which the motion of light rays is simple. So let us choose a new coordinate, a new ingoing coordinate. And it's ingoing because it's defined by the ingoing light rays. And the way I'm going to choose it is just by this equation. So the constant will be my coordinate. So V is equal to T plus R plus RS log modulus R over RS minus 1. You see, if I write out all these ingoing light rays, they look like this. They all have this shape, right? And as I vary the constant, the curve changes, right? So that's telling you that lines of this being constant are coordinates on space-time. And that's what this transformation represents. I go from T and R to V and a new coordinate, and R prime equals R. I want to keep this radius R because everything funny is happening at R equals RS. So let's keep the radial variable what it was. But instead of T, I'm going to change to V. Okay? So whereas I had my coordinates being T and R, this is T and R. These are lines of constant T and lines of constant R. Now I'm going to use lines of V equals constant, which are these ones, and also lines of constant R, which are these ones. Okay? It's pretty obvious that the new coordinates are singular at R equals RS, right? In terms of the old ones. The coordinate transformation is singular because I'm having them all bunch up along this direction. And clearly something funny is happening along R equals RS. The V is not well defined at R equals RS. So what we're actually doing is a singular coordinate transformation which undoes a singularity in the metric. In fact, that's the only way to undo a singularity in the metric. The metric singular, any regular coordinate transformation will leave it singular. The only hope of getting rid of a singularity in the metric is to do a singular coordinate transformation. All right, so that always makes people very nervous. We're deliberately doing something badly defined in order to undo something badly defined. Okay? And we'll justify it a little bit later. So this is singular at R equals RS. Singular at R equals RS. But we're going to have to do that to fix the problem in the metric. Now, if we do that, then for R bigger than RS, there's no problem at all. It's a perfectly good coordinate transformation for R bigger than RS. And what we see is that dV is dt plus dr over alpha. Okay, so dv is dt plus dr plus dr times the derivative of this with respect to r, and it's exactly dr over alpha. You can see that also from yeah, I mean, that really arose right back there where we found the two null trajectories. So dv is 0 along these lines, because these are lines of v equals constant. And so ds squared is equal to minus alpha dv. Oh, so this, from this equation, it follows that dt is dv minus dr over alpha. And so if I plug that into the original metric, then ds squared is minus alpha dv squared plus 2 dv dr plus r squared d omega squared, d omega 2 squared. Okay, let's check that. If this is true, then when I calculate dv squared, I'm going to get minus alpha dt squared. I'm going to get minus 2 dr dt over alpha. So I'm just going to get minus 2 dr dt. But this term will give plus 2 dr dt. And then over here, I'm going to get minus dr squared over alpha. And here, I'll get plus 2 dr squared over alpha. So I end up with my dr squared over alpha. Okay, so that's the metric in the new coordinates in v and r. So we eliminated t, and this makes a lot of sense. You see, the problem I had with my photons is this silly coordinate t was going to plus infinity as the photons approached r equals to rs. So obviously, t looks like a bad coordinate. So let's change from t to some other coordinate. And the nice one looks like v. If we look at this metric, it doesn't look very singular. You see, this metric looks like minus, remember what alpha is, 1 minus, alpha is 1 minus rs over r. And then in these directions, so this is v, r, theta, phi. In the VR direction, it's 1, 1. There's nothing in the RR direction. And then it's the usual things down here. Sine squared theta. The other ones are 0. But the important point is you notice if R goes to RS, this component 0, that component 0, but these two are non-zero. And that means the determinant is fine. Right? The determinant of this matrix, det of that, is minus 1. And so that has one positive and one negative eigenvalue. That's absolutely fine. That's a good metric. It's invertible. Absolutely nothing wrong. Okay? So there is nothing wrong with this metric at r equals rs. Okay, it's still bad at r equals 0. R equals 0, it's obviously singular, but we know we can never get rid of that singularity in any coordinates. So this is a good metric. And in fact, these coordinates are known as Eddington-Finkelstein coordinates. So they realize there is a coordinate system in which there's no singularity at r equals rs. And to follow a photon through, or light ray through r equals rs, I just go to these coordinates, and it sails right through, and there's no problem at all. Okay, so again, I'm always going to graph things in t and r, even though the good coordinates are v and r. You see, if I graph the plot, if v is a constant, which it is on the ingoing null rays, then when I graph this t, I get so v equals constant. That means that t is v minus r minus rs log modulus r over rs minus 1. And now I know where my trajectory goes. So, so in fact, it goes up here, goes to plus infinity as r tends to rs. And then this trajectory, I can now look at this for r less than rs. Again, this is minus infinity. The log is negative. And so it comes in from here. and it goes down and it ends horizontal as it hits the singularity. Okay? So keeping in mind t and r are bad coordinates, we at r equals rs, we can still use them away from r equals rs. And what we realize is that this whole funny business up here is totally resolved by going to the coordinates v. So now I can trace what happens to this photon. It goes in, it crosses the Schwarzchild radius. This is just a coordinate singularity, and it hits r equals 0. However, there was some ambiguity there, right? Why did I choose v? I could have, why did I choose something going like t minus r? Well, I picked one of the two, null coordinates, right? So the null trajectories were dt were this quantity equals 0, or the thing with the minus sign equal to 0. And I could have used that equally well. And that would have given me outgoing light rays. So let's do that as well. And then we'll see there's actually a bit of a contradiction. So outgoing signals, light rays, satisfy dt well, let me just say it this way. For ingoing light rays, this quantity v was constant. For outgoing light rays, this quantity u, which is t minus r plus rs log modulus r over rs minus 1, this is constant. So the way to think of those is these were the ingoing curves. The outgoing guys are these ones. All right, so these are lines of u, and each of these lines are u equals constant. Right, so that whereas the other way, this was the line of v, increasing v, and these lines were v equals constant. So an outgoing null ray kind of has the reverse singularity. It has to have come from t of minus infinity, and then it eventually flies outwards at a slope of 45 degrees. If I did this, you can calculate that ds squared is minus alpha du squared minus 2 du dr plus r squared d omega 2 squared. So just like with the v coordinates, the u coordinates are perfectly non-singular at r equals rs. Also non-singular at r equals rs. But in these u coordinates, if we do translate this null ray coming outwards, then u equals constant is still valid inside r equals rs. And if u equals constant, that means that t is equal to r plus rs log 1 minus r over rs for r less than rs. See? Just a little confused. This is t goes like minus r. And so this is t going like, okay, wait a second. Just getting myself confused. So obviously t goes to minus infinity. This is really a modulus sign in here. T goes to minus infinity. Yeah, so that's right. So t goes to minus infinity as r goes to rs. And then as r becomes less than rs, this minus infinity becomes finite, and t becomes positive again. And it ends up like this, horizontal. Okay, so this is an ingoing u equals constant light ray, goes off to minus infinity in t, and it comes back, and it looks like this.
Aren't we doing outgoing coordinate?
Oh, sorry, outgoing. Thanks. Outgoing. Okay, so the point is the following, that at infinity, I think I know about the direction of time. Okay, so at infinity, I have Minkowski space, and here's a photon which is going forward in time, right? And so if I trace this guy going forward in time, it's telling me that the direction of the flow of time is in the negative t direction inside r equals rs. Okay, so flow of time is in the negative okay, actually r is the time coordinate, of course. It's in the flow of, that's still positive r. Increasing r direction for r less than rs. Okay, so as I said, r is the time coordinate, and according to the outgoing coordinates, increasing r is increasing time. Okay, we tell that because the photon was certainly coming out in increasing time, and so whereas here its radius is certainly increasing, so increasing time is increasing r. But you see, for the ingoing guy, it had increasing time coming in, but then it has decreasing r. So according to these coordinates, in these coordinates, for r less than rs, decreasing r is increasing, is in the positive time, is the positive time-like direction. Okay, so we've got a terrible contradiction. We think r is time-like, but if I follow a photon in, time is decreasing for the radius being decreasing. But if I follow a photon out, time is increasing, corresponds to the radius increasing. All right, so it looks like a terrible contradiction. We don't know what the increasing direction of time is inside rs. Contradiction. But now we're going to resolve it. And it will turn out, yes?
Can I just seek some clarity?
Sure.
So, would it be safe to say there's 4 regions if you consider like we're looking at the outgoing. There's inside the Schwarzchild radius.
Exactly.
And in there, it's or is the time-like.
Yes.
The time-like component.
Yes, exactly.
Outside the
R, yes.
outgoing
Yes.
radius, or is still the time-like component.
R is time-like, but its direction of increasing time is the opposite. So as you said, there will turn out to be 4 regions.
Yeah.
So what will turn out to be the case is that if I extrapolate the outgoing coordinates back into the black hole, I am describing a region of space-time, but it's not the same as that region. There's one region of space-time in which increasing time is increasing R. There's another region which is totally distinct, where this R has actually nothing to do with that R. And this R is decreasing in the positive time direction. So what we've discovered is 2 regions. We thought we only had one region, R between 0 and RS, but actually there are 2, and they have the opposite direction of time. And this will all become much clearer when we write the cross-skull coordinates. So at the moment, I just want you to notice there's clearly a contradiction, that outgoing light rays come from trajectories where R increased in order for the light ray to get out, but ingoing light rays come from trajectories in which R decreases as you follow the light ray. Okay, so it's really very, very puzzling. So it will turn out that both are true. That both are true, but neither is the complete story. So this was really not understood until the late 1950s. In fact, Paul Dirac wrote a paper as late, I think, as 1964, where he doubted the validity of the Schwarzchild metric for R less than RS for exactly these kinds of reasons. So some very clever people doubted that this really made any sense. Now, before we resolve all this, let us notice, so we followed photons into the black hole, we watched them coming out of the black hole, and we seem to have two copies of the interior, one of which time went forward for increasing R, one where it went forward for decreasing R. Now, equally well, you could do the same thing. Start with the metric at R less than RS, follow light rays going, well, yeah, let's say it this way. Let's work in these ingoing coordinates. You see, I've only focused on one trajectory here. What about if I took the other trajectory? There is another trajectory in these coordinates. And of course, what it looks like is, okay, let me just, yeah, I'll work it out. So what does the other trajectory do in the ingoing coordinates? So we can have, obviously, if we just look at the metric in the ingoing coordinates, we studied dv equals 0. That's a null trajectory, right? But you can easily see that there's another way to get a null trajectory, which is that dv is 2 dr over alpha. There's a second null trajectory. dv is 2 dr over alpha. We can integrate that to get v is 2 times r plus rs log mod r over rs minus 1. plus constant. And this equal, and v, of course, is in the ingoing, v was defined by this formula, t plus r. T plus r plus rs log mod r over rs minus 1. And so you conclude from this that the second coordinate, the second null trajectory in the ingoing coordinates looks like this. Okay, plus constant. And if we sketch it, so this is basically t being minus r. The second trajectory is t goes to plus r. And so it comes, let me see. Yes, so it would be coming out of the black hole. So we're in the ingoing coordinates, but the trajectory is coming out of the black hole. And then this one is, okay, let me try and, wait a second. Yes, sorry. So let's stay in the ingoing coordinates, but inside the Schwarzchild radius, we have these two trajectories, right? Both of them have the same direction of time because r is decreasing. Okay, that's positive time direction. So this trajectory and that trajectory are the two null trajectories which have r decreasing. If I follow this guy out, where does it come from? It comes from this guy going backwards in time. So now I've got my ingoing null ray going forwards in time, but I also have an ingoing null ray going backwards in time. So it's telling me that even out here at infinity, the direction of time increasing doesn't agree for these two photons. So the conclusion there is that if I stick to ingoing coordinates, I actually have two copies of the outside space-time, right? So I got a lot of copies, right? I went in and I discovered two versions, depending on the coordinates, one of which are decreasing is increasing time, one of which are increasing is increasing time. And now I just did the reverse. I stayed inside the black hole, and I followed photons to the outside. And I found that photons which were going one direction of time inside the black hole corresponding to two different directions of time in the outside of the black hole. So it's telling you that there is an outside version of space, outside version, which has the arrow of time reversed. Okay, so it's all terribly confusing, but hopefully now will become crystal clear. So let's put this together. And this was done by Martin Kruskal. Interestingly, it was done by him when he was an undergraduate. And he was learning GR somehow and fiddling around with coordinate transformations. And he figured this out, and then he went to graduate school, and somebody said, oh, there's this terrible problem at r equals rs. And he said, oh, no, that's not really a problem. They said, oh, that's very exciting. And so they made him write the paper up. It's in Physical Review. Well worth looking at. 119, 1743, 1960 by Martin Kruskal. He then went on to do other things. He kind of invented the concept of soliton equations. This was the state of play before he started fiddling around. And so the idea is very, very simple. It's in fact given by exactly this picture. You see, the u coordinates were good, not singular. The v coordinates were good, not singular, at r equals rs. So let's use both of them. And forget about t and r. I mean, we're getting all this confusion about the direction of time and r and t. Maybe they're both lousy. So let's change, let's to use u and v and give up on r and t. So for r bigger than rs, where everything is clear-cut, none of these coordinates are singular, let's now do our coordinate transformation outside rs, and then we'll try and get some good coordinates that are just valid everywhere. Okay, except at the singularity, of course, r equals 0. So, well, they're good there, it's just that the metric is singular. So v is t plus r plus rs log r over rs minus 1. U is t minus r minus rs log r over rs minus 1. And we're only doing this for r bigger than rs. And this one is constant on outgoing light rays. This one is constant on ingoing light rays. We also have that dv is equal to t plus dr over 1 minus rs over r, and du is dt minus dr over 1 minus rs over r. So it's easy enough to see that this means that the line element is minus 1 minus rs over r times du dv plus r squared d omega 2 squared. And what is r in that formula? So when you write a metric down, you'd like the coefficients to be functions of the coordinates. R is defined from these equations, where r is defined by r plus rs log r over rs minus 1 equals v minus u over 2. Right, so that's a kind of nasty equation, but it's a perfectly good equation. If I think about the left-hand side, just some function of r, right? And so basically it's linear in r, but plus this logarithm, which goes to minus infinity as r goes to rs. So here's this function, and this is a function of r, and this is rs. This is r equals rs. This is r equals 0. So there's some function of r is equal to v minus u. You see, this is only really going to be valid for some range of v minus u, but let's not worry too much about that. Let's just plow on. So if I take this formula, I get r over rs minus 1 is equal to, actually, let's write it the other way around. I'll write it as 1 minus rs over r is equal to rs over r times e to the minus r over rs times e to the v minus u over 2 rs. Okay, so what did I do here? I divided by the rs. I took this term over to the right-hand side, and I exponentiated the equation. So I got r over rs minus 1 equals e to the minus r over rs e to the v minus u over 2 rs. And then I just multiplied by r over rs to get this equation. Why am I doing that? Well, I want to rewrite the metric in terms of u and v. So my ds squared is equal to this guy. So now I've worked out the coefficient. We can see it's minus rs over r, e to the minus r over rs, e to the v minus u over r over 2rs times du dv plus r squared d omega 2 squared. Why did I do that? Well, this all looks beautiful. This is totally non-singular for all r except r equals 0. Right? This is absolutely fine. And this is also absolutely fine. This is exponential, so it's always positive. So there's no 0 anymore at all. This looks really great. And then the final step is to say, I can simplify this a lot by defining, so let's do that on another board. So this looks absolutely and completely fine at r equals rs. But an even a nicer simplification is to define u, capital U, to be capital U to be rs e to the minus u, little u over 2rs, and v to be rs e to the plus v over 2rs. Okay, and in terms of these coordinates, ds squared is equal to plus 4 rs over r e to the minus r over rs du dv. Okay, so d capital U is going to bring out to d little u over 2rs. The rs's will cancel, so I'll get a half. I'll get a minus sign. And then d capital V will do the same. I'll get another half. So multiply by 4, I get exactly this term. Okay, plus r squared d omega 2 squared. And now there's a final step, which is that the du dv suggests we change coordinates to make it look like Minkowski. You know that if u is x minus t and v is x plus t, then du dv is equal to dx squared minus dt squared. All right, so that's Kruskal's final step, which makes this look pretty much like Minkowski with just an overall factor, dx squared minus dt squared plus r squared d omega 2 squared. And so this is the Kruskal metric, completely equivalent to Schwarzchild, certainly for r bigger than rs, but this makes perfect sense even for r less than rs. But the trick is now to work out what on earth is this r variable. So we have everything we need because we have somewhere, let's see, we have uv. So this is u times v is rs squared e to the v minus u over 2rs. And this we had in terms of r, right? So we know it in terms of r. this is r squared, this is rs squared, e to the r over rs times r over rs minus 1. So that defines r of x and t. Okay, so uv is that, which is, of course, x squared minus t squared. So this defines the quantity r in the metric in terms of x and t. So we now have a beautiful metric. It's a function of x and t. R is a function of x and t. It's not static, not obviously static. There's no symmetry in t, but it has no singularities at r equals rs. And likewise, we have t is u plus v over 2, and that's rs log capital V over capital U, and that's rs log x plus t over x minus t. Okay, so now I'm going to draw a picture of this metric, and this will hopefully make everything completely clear. So the important point is that in that line element, there's no singularity at r equals rs. But in order to picture the metric, we need to draw things in the tx plane. So this is t, and this is x. And now let's think about this coordinate little t and try to interpret it. So you see that, in fact, what I want to do is slightly change that formula. I want to put a modulus sign in there. I need to. So strictly speaking, we derive this only for r bigger than rs, but I can do that. Okay, if I do that, then for all values of x and t, the t coordinate will be a real number. Okay, so what do you notice about it? Well, this is the line t equals x. Okay, it goes off here. This is the line, whoops, this is the line t equals minus x. And you see that on both of these lines, t is slightly problematic. Okay? So if t equals x, the denominator vanishes here, and so little t goes to plus infinity. So on this line, t is plus infinity. If t is minus x, the numerator goes to 0, so t is minus infinity. Little t is minus infinity. So that whole line is little t is minus infinity. Right, so now things are beginning to make sense. Well, let's do r. Look at r, this equation, right? So the right-hand side is a function, so this e to the r over rs, r over rs minus 1. What is this function? Well, it's positive if r is bigger than rs, and it grows exponentially, and then it goes to minus 1 at r equals 0. Okay, so this is r. So what we're saying is that x squared minus t squared is some quantity which has to be bigger than minus 1. if I take the limit -1, at this point, x squared minus t squared, if r is 0, right, x squared minus t squared is minus rs squared. What is that? Well, that's the equation t squared is rs squared plus x squared. That's the equation for a hyperboloid. Okay, so that looks like this. T up here. This is t equals plus square root x squared plus rs squared. There's another solution, which is down here. This is t equals minus square root rs squared plus x squared. Okay? And those are r equals 0. That's a singularity. So we're never going to get rid of that. So anything beyond here has to, that's through the singularity. Okay, so this is r equals 0. This is r equals 0. That's also r equals 0. So now you're beginning to see there are actually 4 regions of space-time. Okay, there's the exterior, which we had initially. And if I send in a light ray, it's going to just, by the way, in these coordinates, light rays, radial light rays move at 45 degrees, right? So in these coordinates, dx is plus or minus dt. A radial light ray satisfied dt is plus or minus dx. They move at 45 degrees. So if I send in a light ray, well, it just goes straight in, and it hits r equals 0. But notice what it's doing. It's going through t equals plus infinity, and it's coming out of t equals plus infinity, and then so actually lines of constant t look like this. This is t equals constant. And so it goes to t equals plus infinity, and then it decreases in t. So that was our original ingoing guy, right? So it went up to t of plus infinity, and then it decreased in t. It doesn't matter because t is not a time-like coordinate, so t is plus here. T is a space-like coordinate here, right? R is the time-like coordinate. This is r equals 0, and this is r equals rs. And so decreasing r is increasing time. Okay, the light cones in this picture are always like this. So if I've got an ingoing null ray that's increasing time, that's what it's doing. So likewise, we studied outgoing null ray, and we now see it came from a completely different place. Okay, so it came from inside r equals rs. By the way, this line is r equals rs. Both of these lines are r equals rs, and t equals either plus infinity or minus infinity. Let's see that from the picture. You see, if x equals plus or minus t, in other words, I'm on one of these lines, then r equals rs. Okay, so our outgoing null ray actually came from here. Nothing to do with this. And it came from a direction in a place in space-time where increasing r is increasing time. Because r is 0 here, r is rs there. Likewise, when I followed my null ray backwards in time out of the black hole, I was doing this. But I had another one. And that other one is just coming here. So there's a second copy of the exterior. This is a second copy of the exterior space-time. And notice in this copy, t, the coordinate t, increases going in this direction, because this is t equals plus infinity. this is, sorry, t equals minus infinity, and this is t equals plus infinity. Okay, so you can think about this as a universe where time marches this way, and this is a universe where time marches this way. So I should actually draw this. Let me see. Increasing r is increasing, decreasing r is increasing time. So, so this trajectory comes out of, so which way does the arrow go? Yeah, it also goes this way. Yes, it goes this way, so they're both going forward. Yeah, obviously. This is the light cone, so they're both the forward photons, but when I follow it back, I go into another copy of the space-time. Okay, so I think that's all I wanted to say. It's very mysterious. One should perhaps also draw the picture for what happens in a realistic case. I mean, do all these regions really exist? You know, if this is a black hole, what is this? The black hole is something, you know, is an object. This is called the event horizon, which we could fall into. This is the time reversed black hole. So this object is called a white hole. Okay, because anything that exists inside the white hole has no option but to leave. If it's time-like, it has to leave the white hole. These are not observed in the universe. Okay, so this is not a physical solution. It is a solution of the Einstein equations, but it's not physical just because we've never seen a white hole. This part is the black hole. So in the realistic case, if you have a star which collapsed, okay, then of course the Schwarzchild solution is not valid inside the star. It's only valid outside the star. So let's say we had a star. There's some other solution inside the star. So the existence of the star shields us from all this white hole phenomenon. There is no white hole. But outside, the Schwarzschild solution is perfectly valid. So let me just think. Yes, it must be. I have to draw it like this. I've got to shield away all that Schwarzschild solution. So we would never see this part of it. Okay, this is the collapsing star. Collapsing star. And when a star collapses, you do form the event horizon. And then you form the singularity in the middle of the black hole. But inside the black hole, the star, the material of the star is going to collapse to the singularity. It has no choice but to collapse to the singularity. And of course, there's a big question mark. What happens there? So in realistic stellar collapse, we don't have these four regions. We only have one region of the Schwarzschild black hole, and that's mysterious enough. Okay, I think, are there any questions? I hope that was confusing. Yes.
Is there any reason a white hole couldn't exist?
No. It would be very, well, you say any reason. Within general relativity, it's a perfectly valid solution of the field equations. But you have to decide whether these solutions are physical or not. If a white hole could exist, there would be problems with the second law of thermodynamics. But you know, that's a whole set of other arguments. there would be problems with predicting anything if white holes existed, because you see, when I look back into the white hole, everything I see comes straight out of the singularity. So if I could see a white hole, I would be able to observe the singularity. And because the laws of physics break down here, and because I can't predict anything. You look into a white hole, and you see something we can't predict from the laws of physics. Okay, so that, again, you could say maybe that's a reason why we're not allowed to see white holes. With black holes, the fact that GR breaks down here doesn't really affect my ability to predict anything outside the black hole, because I can never see this. See, if I travel out, if I keep outside the black hole, outside R equals RS, I'm always, all I can observe is the exterior space-time. I can never see that. But no, one should just say it's a very deep mystery why black holes exist, but their time reverse solutions don't exist. White hole is literally the time reverse black hole, and it doesn't exist.
If one did just like pop into existence, would it immediately just disappear pretty much?
No, it would destroy everything. It would destroy everything. Because you've got the singularity, which can emit who knows what. You create something, and unlimited stuff would come out of it. There's nothing which limits what can come out of a white hole.
But also, we're not sure yet if we cannot have net singularity. Like cosmic censorship is not something that's.
I mean, none of this is for sure. There are very few solid statements. People make conjectures, but
Black hole size is limited by its like
mass.
Not exactly mass, right? Because there's not. But yeah, basically. So why couldn't a white hole be limited by that too?
Because, well, there's a very big difference, because in the white hole, it affects us. The black hole, the interior of the black hole has no effect on us at all. The stuff went in, and then it never affects us. I mean, the stuff inside here, even somebody here, can never, we live here, we live outside the black hole, we live in this part of the space-time. Nothing can go faster than light. So whatever happens inside the black hole can never affect us. On the contrary, everything happening inside the white hole affects us, or can affect us, including the singularity. So if white holes existed, it would just say you can't predict anything using GR. So you really have no idea what to do with the singularity.
What if there was one that was so far away that we couldn't see it yet?
No, it's everywhere. Okay, so the white hole can affect the entire exterior space-time. This singularity goes off all the way down the light cone. Okay, so this singularity goes off here. And so when I stand anywhere outside the black hole and I look in, I see the singularity. You can't avoid it.
We just haven't found it yet.
Well, that suggests they don't exist. It suggests they don't exist. Yeah.
So is our black hole the second copy's white hole?
Our black hole is, yeah, so you mean is this interior? Yeah, so I think, I mean, in the solution, a single interior corresponds to two exteriors. It can be influenced by this so in other words, imagine I fell into the black hole. As I cross inside, I would be influenced by anything going on out here. So, there's another universe out here. There's two universes. And as I fall inside, I might receive radio waves from somebody in the other universe.
Why is the arrow on the left not pointing outwards if time is going down?
No, time, at large radius, we can try, so this is capital T, but we should see that at large radius, that is related to little t. Let's see, where do we see that? We have to basically invert these formulae. Well, let's fix the radius. Let me see. There is an easy way to see this. Yes. So at fixed r, that right-hand side is fixed. And so lines of fixed r are x squared minus t squared equals constant. Okay, so one of those lines is the singularity, but there are lots of other lines like that. So fixed r inside the black hole looks like this, as r increases from 0 to rs. And then outside the black hole, these are the lines of constant r. Okay, so if I sit at fixed r, then okay, let's see. Oh, yeah, so the lines of constant t go from lines of constant t. See, if t is constant, you can show from this equation that the slope of x versus t is constant. So actually, these are the lines of constant t. Okay, they're just straight lines. X over t equals constant. So this is t increasing. All right, so I sit out here. My little t coordinate is increasing in this direction, and that's the same as capital T. But if I sit out here, little t is increasing in this direction, the opposite to capital T.
Yeah. So
Capital T is the right coordinate system. So, I mean, it's a better coordinate system. Yeah, so I shouldn't really, the direction of time is this way throughout this picture. Yeah, I shouldn't have drawn it the other way. The direction of time should be determined by picking non-singular coordinates and then consistently, identifying the future and the past light cones across the whole diagram. But the statement is that, so what I should have said is that increasing time is this way, but that's saying little t goes from plus infinity to minus infinity over here. Increasing time is little t goes from minus infinity to plus infinity. Yeah.
So the fact that we have the collapsing star
Yes.
tells us that probably the lower part
doesn't exist.
What about the left part? You also think?
Yeah, also doesn't exist. Also doesn't exist. So this is very, this ever since this was discovered, people have debated what on earth it means. I would just have to say that nobody really knows. In fact, I had some funny experiences in my career meeting with people who worked on these solutions. So one of them was Chandrasekhar, who's a very famous astrophysicist, worked out all the theory of stars and everything. And I was talking about very speculative modern physics ideas, something called cosmic strings, which would be a test of grand unification. And, I made some jokes, and these are very hypothetical theories, and obviously we hope these objects exist, and if so, we'll learn something. And he came up to me at the end of the talk. He said, you have a choice to work on two things. A theory which is probably wrong, okay, but might be testable, okay, or a theory which is definitely right, okay, and but can't be tested. I said, and I would strongly encourage you to work on the second, because then you at least know that what you're doing is correct, even if it's not physical. Okay, so it's very funny that this guy made real predictions for stars and he transformed astrophysics, but he seriously believed that to work on something correct but untestable was worthwhile. And I said, I'm sorry, but that's not what I'm interested in. I'm interested in nature. So I'm quite happy to make speculations if they're testable. But I don't want to go into Alice in Wonderland with general relativity. And this is just the beginning. I mean, once you study rotating black holes, it gets much more interesting. And charged black holes. So typically you find you go inside, and then you come outside into another universe, and then you can go back inside the black hole and come into a different universe. And, it becomes infinitely more complicated than this this setup. So I would just say at this point, this is still very mysterious. We don't quite know what it means. The singularity tells us general relativity is wrong. Okay, so I disagree with Chandrasekhar. We know the theory is wrong. We hope that quantum effects resolve the singularity. Do they lead to a bounce? Some people believe, like Lee Smolin, that when you fall through the singularity, you're going to go through this is a big crunch, and there'll be a big bang afterwards. Okay, but there's no mathematics behind that. It's kind of wishful thinking, and lots of other speculations. So that's what makes it exciting, but also quite sort of challenging. So I think now we can actually see black holes. This has all become much more real. We know these things are there. We know this deep mystery is there about the universe. And we know that quantum gravity is absolutely relevant here. Quantum gravity is important, but we have no theory yet of quantum gravity. Okay, so I was going to show you a little movie. Do you want to see the movie?
Yeah.
Okay. So this is falling into the black hole. Yeah, I should mention a little bit more. You know, if we live out here, we cannot travel into the other universe, right? Because that would require us to go faster than the speed of light. The best I can do is to zoom here and hit the singularity. That's if I go at the speed of light into the black hole, I'm only going to succeed in hitting the singularity. Okay, if I could go a little bit faster than the speed of light, I could come out and, but you can't do that, okay? Nevertheless, some very serious theoretical physicists, in particular Leonard Susskind, Juan Maldacena, et cetera, take these two parts very seriously, all right? And they try to imagine this is somehow important in the resolution of the black hole information paradox. I am personally completely unconvinced, but a lot of people write a lot of papers about this. Yeah.
Do these, does anything change when you add in mass?
Yes, everything changes. So this solution here assumed T mu nu was 0. We solved this equation. By the way, I didn't emphasize this, but having found the Kruskal coordinates in which there is no singularity in the metric anywhere in this region, right? You could just throw away the original coordinates. Who cares? Schwarzchild coordinates, you just say they're bad coordinates. Stick to Kruskal, it solves this equation. You can just check, plug it back into this equation, it solves it. So this Kruskal solution is perfectly valid solution of the Einstein equations, but only if T mu nu is 0. So all it can describe is the exterior of some spherically symmetric mass. Okay? And actually, if I just write it down as it is, there's no mass here, right, anywhere. T mu nu is 0 everywhere. So you have to assume this is the metric of something which has since disappeared behind the singularity. Okay, this is empty everywhere. When you do the solution for a star, this is what I was trying to draw here, the equations we solved are no longer valid inside the star. So the only part of Kruskal that we can trust is this exterior part. But that's fine. There really is an event horizon. All that part is completely trustworthy. Although, as I mentioned, people like Dirac doubted this. You see, when you try to ask, what mathematics am I actually using to get across the horizon, you're actually using analytic continuation. Okay, so what you really are doing, you've got a bad coordinate system. You're trying to improve the metric. This is strictly speaking only justified if everything is analytic. And you saw we have those logs, and we're allowing ourselves to take moduluses and stuff like that. So in other words, I'm allowing myself, one way to think about it is I know some solution outside the black hole, which we think is physically relevant, the Schwarzchild one. I'm allowing myself to change coordinates to Kruskal in a certain region of space-time. And then I analytically, then I continue the Kruskal coordinates through. And I believe the answer. Okay, so you're relying on the fact that I'm allowed to analytically continue things that are not, that have singularities. I continue around singularities, yeah.
So the universe with the time moving backwards, that's just a mathematical artifact, right? No one's like claiming there's actually another universe.
No, as I said, some people think it's really there. Some people think it's relevant to solving the black hole information paradox. Yeah.
You were mentioning that r mu nu equals 0 doesn't indicate anything about mass.
Yes.
But then what fixes the length scale that is Rs?
Oh, that's just a constant in the solution.
Right. So it's the same diagram.
It's an arbitrary constant.
Arbitrary Rs.
Yeah, exactly. So if you just change Rs, all you're going to do is change the location of this hyperboloid. It's the same solution. Yeah, I mean, the Planck mass never comes into classical gravity because it's, as you see, in the equation, it doesn't even enter. So the Newton's constant doesn't enter. So there's just some constant, which we call Rs. It's not associated with the mass. Yeah, that's right.
If the length scale is sort of a constant, then r mu nu equals 0 allows for arbitrarily large Rs?
Yeah, any Rs. Any Rs at all, exactly.
Send it to infinity.
Black hole can be as big as you like. The way physically you would measure the mass of the black hole is by sitting off here at a large radius, and then you'd see the metric goes like minus m over r, and you'd say that's the Newtonian potential, so it has a mass m. So the Rs does determine the long-range metric, and that you interpret as the mass. But there's no mass appearing in the equation of motion, just an integration constant. Okay, so let's see this funny movie. My computer hasn't died. Here we go. Is the screen working? You turn the lights off. Is the projector on?
It is.
Oh, it is. Okay, I just need to. Thank you. That's great. So, that's all. Oh, I haven't plugged it in. My fault. Sorry. Where is the plug? Here we go. Okay. There we go. All right. You probably know this YouTube channel better than me. Okay, so you may know that we're about to launch the Center for the Universe, not the Center of the Universe, because that's each one of you, in November. So that should be a very fun event. I've resisted talking about cosmology throughout this course. Because that's the field I really love. I would not shut up at all if I talked about that. So, thanks for coming. I really enjoyed lecturing you. I hope to meet you throughout the year. Please come and bother me. Tell me what you're interested in, whether you're having fun, whether you're not having fun. My door's always open. And take care. Have a lovely weekend. Okay.
And this is what you tell us about 3 weeks of relativity. Schwarzchild, teenager, and smashing your business.
Okay, thank you very much. And thanks again to